Till this point, the atomic model we have learned about in schools and colleges have been like this. However, recent discoveries supported by artificial intelligence have proven that the fundamental understanding of proton structure in atoms is wrong. Based on their calculations, scientists have found that in addition to up and down quarks, charms quarks is also detected in protons. However, what makes this discovery intriguing is that the charms quark's mass is about 1.5 times greater than that of a proton. This implies that theoretically, the likelihood of a charm quark being inside the proton is almost impossible. On the contrary grounds, there is a substantial evidence supporting the occurrence of such events, and this phenomenon has been observed since the inception of atomic models. In 1900, people believed that the atom was the smallest particle, but in 1911, Ernest Rutherford conducted a gold foil experiment which revealed the structure of atomic particles and their positions. By colliding positive alpha particles with gold foil, Rutherford observed that the most particles passed through while some were repelled, indicating the presence of a positive charge in the repelling point. This led Rutherford to propose a new atomic model with positively charged protons or neutrons in the nucleus and electrons revolving in circular orbits around it. However, Rutherford's atomic model had a significant flaw, later addressed by his student, Niels Bohr. According to the classical physics, electrons revolving in circles around the nucleus would emit radiation, leading to a decrease in the energy and eventual collision with the nucleus, rendering the atom unstable. Niels Bohr revised this concept in 1913, introducing a new atomic model. According to the Bohr's theory, electrons do not emit energy while revolving in a specific stationary orbits. Instead, radiation occurs only when the electrons transition between orbits. The theory is now widely accepted due to its genuine explanation and supporting evidence, initially suggesting that there might be no need to delve further as scientists believed they had already discovered the most useful particles and understood their mechanisms. However, in 1936, a significant discovery occurred when the physicists found a particle similar to the electron, but with a greater mass. This pivotal moment took place during the experiment conducted by American physicist Carl David Anderson. He created a cloud chamber, nearly freezing water vapor, and passed highly energetic particles through it. In this experiment, they detected particles that shared a negative charge with electrons but possessed a higher mass, leading to their classification as a new particle called the muon. Following this discovery, scientists uncovered several other particles whose properties did not align with either protons or electrons, leading to a significant increase in the number of these particles. Then, later in 1964, physicists Johann Zwingli and Murray Gell-Mann proposed a groundbreaking theory that challenged the notion of the fundamental particles. They suggested that all particles, including protons, were composed of elementary particles called quarks, which dictated their quantum properties such as charge and spin. While Zwingli and Gell-Mann had theoretically calculated some properties of quarks, experimental proof was still lacking at the time. The concept of the quark was initially a mere hypothesis, but in these years between 1973 and 1976, scientists conducted numerous particle accelerating experiments at the Stanford Linear Accelerator in California. These experiments involved colliding electrons with protons at high speeds, allowing them to break protons and detect the particles within. Through these experiments, they made a groundbreaking discovery that protons are composed of 2 up quarks and 2 down quarks, interconnected by gluons, which are particles responsible for mediating a strong nuclear force. The particles they studied were incredibly small, requiring multiple experiments at varying electron speed to detect gluons effectively. In a particular experiment, an unexpected finding was made. The presence of a charm quark was within the proton. This discovery initially challenged the prevailing belief that protons were made up of only 2 up quarks and 1 down quarks, totally 3 quarks, since the charm quark's mass exceeded that of the proton. However, quantum physics has evolved since then, raising a new question about the proton's internal structure. According to the quantum physics, protons lack a fixed structure and are not solely composed of 3 quarks. Instead, they have a quark C containing various quarks and antiquarks. to maintain the properties of protons such as color, charge, and spin, and ensure stability. These quirks cancel out with their corresponding anti-quirks, leaving only the three quirks that have been widely studied. With both the theory and observations from SLAC in hand, scientists have delved deeper into the study of protons. Today we are aware of 6 types of quirks: up, down, strange, top, bottom, and charge. Among these, up, down, and strange quirks are considered lighter, while top, bottom, and charm quirks are on the heavier side. Since the charm quirk is relatively lighter in the group of heavier quirks, scientists initially focused on detecting it within the proton model, and after that, scientists also utilized the world's largest proton smasher, the Large Hadron Collider, to dwell into the proton model and study elementary particles. By colliding protons at higher speeds in the collider, they encountered some intriguing results. Particularly, they discovered charm quirks in these collisions, but were uncertain whether these quirks were intrinsic or extrinsic. Intrinsic quirks are naturally present in protons, while the extrinsic quirks are created due to external factors. In the result of that, several scientists speculated that the quirks were products of gluon splitting, which is responsible for holding particles together. As the gluon splits, quirks forms as a consequence. These quirks are essentially the result of how gluons behave at high energies. However, based on these findings, there was a belief that charm quirks might exist at low energies as well, prompting further research. Manual exploration of this concept would have taken many years to yield accurate results. The breakthrough came when they realized that they could leverage AI to accelerate the process. By empowering AI, they could simultaneously test hundreds or even thousands of proton models, which finally provided them with the answers they had been seeking. For the AI testing, they trained the neural networks to analyze proton collision data collected over the past 35 years. Each fundamental particle has its own wave function, representing its physical state. Scientists fed the wave function of up, down, and charm quirks in the AI and analyzed the proton collision data. They used a neural network with the 3 layers: an input layer receiving the input data, a hidden layer performing the necessary computation, and an output layer predicting the outcomes. To illustrate this process better, imagine the wave function of the charm quirk represented by a circle, the down quirk by a triangle, and the up quirk by a square. The neural network's analysis involved intricate interactions between these representations, ultimately leading to a valuable insight into the behavior of the charm quirk. Now, to understand exactly how this process happened, let's consider the circle and explore the process step by step. Initially, the circle is divided into pixels, and each pixel is transmitted individual neurons in the input layer. The alternative neurons in the input layer are connected to the next layer through the channels, each with its unique weight. This weight is then multiplied by the input layer's data, and resulting output is sent to the neurons in the hidden layers. These neurons add the respective numerical values to the incoming input layer data before passing through an activation function. The activation function determines whether a specific neuron in the hidden layer should be activated or not. This activated data is then forwarded to the output layer, and this entire process is known as forward propagation. In the output layer, the neuron with the highest value becomes activated, leading to the detection of the final output. In scientific endeavors, researchers have employed the wave function of charm quirk to identify its presence in a proton. Remarkably, after analyzing data for the past 35 years using artificial intelligence, scientists confirmed the existence of charm quirk in protons. The remarkable discovery prompted theoretical physicist Tim Hobbes to propose constructing an electron-ion collider to obtain solid evidence of charm quirks in proton. This decision was influenced by the success of a Large Hadron Collider, proving the existence of the Higgs boson particle. Like other particles, the Higgs boson travels within its own field known as the Higgs field. Interestingly, famous scientist Stephen Hawking warned about the potential instability of the Higgs field, which, if triggered, could lead into destruction of the entire universe. If you enjoyed this video, kindly like and subscribe, and don't forget to share your thoughts in the comment section below. See you in the next one.